So our next speaker is Danielson. So Daine is going to talk about horizons as eavesdroppers. So please, Daine, the floor is.
Yeah, thanks. Thanks, Rick, for the introduction, and thanks for helping organize this very informative RQI circuit. I'm going to be talking about some recent work done with Gautam Sadashandran and Bob Wald, and also some more recent follow-up work to appear soon with Jonah Kudler-Flam. And most of what we'll see today, can be found in these various papers listed at the bottom of the screen. And the punchline, as you can see from the title, is just to understand that horizons as instruments or generators of quantum decoherence, or horizons as eavesdroppers. So I'm going to begin with a thought experiment, which will help to motivate why you should believe that horizons are eavesdroppers before we do an explicit calculation and show them to be such. So imagine that I had a spatial superposition of a massive or charged body. It was created, let's say Alice is the experimenter with the superposition, and she created this superposition far in the past. So that's coming in on the space-time diagram from off the screen in the far past. She's used a Stern-Gerlach apparatus to put this particle in superposition. And as she enters this causal diamond that I've outlined with dashed lines, Alice is going to attempt to recombine the left and right branches of her superposition, so that by the end of the causal diamond, she's going to perform some kind of interference experiment and look and see whether her superposition has remained coherent or not, which I've depicted with this cartoon of either a particle-like Gaussian or a kind of more wave-like interference pattern. More concretely, Alice could implement such an experiment by, if her spin was a superposition in the z direction, she could measure the spin along the x-axis, and assuming she controlled the phases of her superposition sufficiently well, she would know that the state of her system after the spatial superposition was recombined would just be an equal superposition of spin up and spin down in the z direction with uniform phases, which of course is a definite spin up in the x direction. So if she even one time measured in the x direction something other than spin up, she would know in one shot, in that instance, whether or not her particle had remained coherent. So this is a practical way she could, in principle, determine her coherence. Okay, so Alice's particle, of course, is entangled with its own Newtonian field. Formally, you can describe this as kind of tensoring in some coherent states of the field psi1 and psi2 of the linearized graviton field, say, with Alice's particle. And so imagine now you've got this Newtonian field attached to Alice's particle, and in a space-like separated region from Alice's recombination, there's an experimenter, Bob, who's going to attempt to measure Alice's superposed gravitational field just by releasing a particle from a trap and allowing the particle to evolve, and it'll evolve into a superposition of trajectories depending on which Newtonian field it's in. And so that'll tell him which Newtonian field his particles become entangled with, and therefore he can learn which path information about Alice. Okay, Bob, of course, doesn't have to release his particle from a trap. He could keep it in the trap if he wants. He has this free choice of doing a measurement or not. If Bob successfully measures the field, then Alice's particle has to be decohered in the which path basis. But Alice can tell whether her particle is decohered at the end of her experiment by this interference problem this interference protocol that she follows. And this seems paradoxical. because, of course, Bob is doing everything at a space-like separation from Alice's process. So it would seem as if Bob could affect the decoherence of Alice's particle by choosing to release or not release his particle, choosing to become entangled or not entangled with the field sourced by which path Alice is on. Okay, so obviously there are no, the paradox is resolved. This paradox is resolved in an interesting way, though. So in quantum gravity, linearized quantum gravity, and also in QED, where you can pose the equivalent paradox with charged particles, the vacuum fluctuations of the metric, or of the electromagnetic field, are vital to resolving this apparent conflict between complementarity and causality. So really, Bob has to resolve the position of his particle better than some uncertainty, little delta x, but that has to be bigger. That separation of his particle, little delta x, has to be bigger than the intrinsic uncertainty on the position of the particle due to vacuum fluctuations. So even if he controls the wave function of his particle, its center of mass, degree of freedom, kind of could be localized as well as possible from the point of view of quantum mechanical dispersion, there's an unavoidable amount of uncertainty that places a bound on the precision of his measurement, just due to the fact that it couples to a quantum field, and that introduces vacuum fluctuations. So that means that Bob can't perform the measurement, even in principle, over an arbitrarily short amount of time. There's a fundamental limit on how long it takes for him to resolve which path his particle is going into. That's dictated just by the quantum field he's coupling to itself. And meanwhile, Alice needs to avoid decohering herself. Of course, if Alice does a bad job of her experiment, then she could radiate gravitons or photons off to scry, and she would decohere herself. So she needs to do the experiment adiabatically to avoid as much radiation as possible. But this ends up having the effect, well, you can quantify this. You want to make sure she emits a number of entangling photons, the expected number of entangling photons that's much less than 1. If Alice goes slow, then she can minimize this number of entangling photons, just because she can have less and less radiated power. But Bob has to measure from farther away, because, of course, the protocol is that Bob has to be outside the causal diamond of this recombination process, which is when Alice is moving her particle. So the slower Alice goes to avoid decohering herself, the further away Bob is. The further away Bob is, the weaker the Coulomb field or Newtonian field is that he's trying to measure. And so the longer he has to wait before the relative displacements of the two superposed paths of his particle will overtake the uncertainty due to vacuum fluctuations. And it turns out all of these things exactly perfectly balance, as we showed rigorously in a paper in 2022, so that there's no causal paradox. Okay, that's great. But what if we weren't everything we've done so far is in flat spacetime? What if we run the same analysis in a black hole spacetime? So what if Bob is behind a horizon? Well, now something has changed. I just told you that Alice has to perform her experiment as slowly as she can, or she would like to perform her experiment as slowly as possible. But this is going to force Bob to make measurements at farther and farther distances, which are more and more difficult for him to make. But that statement is not true if there's a black hole in the spacetime. In the exterior of a black hole, Alice can take an arbitrarily long amount of time. She can do her experiment as adiabatically as she likes, as slowly as she wants. And Bob could, nevertheless, as is kind of evident from this Penrose diagram, Bob could be just behind the event horizon of this black hole, even if Alice takes an unboundedly long time to do her experiment. So Bob is no longer forced to be far away. He could be just right over there behind an event horizon. So this sounds like a problem because now, I'll make the black hole big. There's no fundamental limit on Bob's ability to resolve which path Alice's particle has taken. And there's no fundamental limit because he can, make the black hole big enough that he can integrate up for however much time he wants. And Alice can take as long as a time she wants because, and Bob is not forced to go any further away from Alice. Okay, so this seems like a paradox again. And we were puzzled by this, but we noticed there would be no paradox if one thing were true. There would be no paradox if Alice was decohering at a constant rate, as if she were becoming entangled with any number of optimally sensitive experiments hidden behind the black hole horizon. So if the black hole decoheres Alice no matter what, just due to the existence of the black hole, then there would be no paradox because Alice can't possibly learn about the presence of Bob, because Bob might be there or not, but Alice will decohere the same way. And this is, in fact, true, and this is what I'll show in the rest of the talk. So, okay, suppose Alice is now doing the same experiments before, but she's in a stationary laboratory outside a black hole. Now, why would this be different from flat space-time? And I gave you this kind of paradox reason, but more concretely, what's the difference? So let's warm up with displacing a classical electromagnetic charge outside a black hole horizon. I'm going to use the electromagnetic case for the explicit calculations just because less indices, it's a simpler calculation. So in Maxwell's equations on the horizon take this very nice form. It says that the time on the horizon, this V, big V is affine time measured along the horizon. The time derivative of the Coulomb field sourced by Alice's particle will be equal to minus the angular divergence on the spherical cross sections of the horizon of the electric field. But if you think conceptually about what this is, these capital A indices are angular indices. So this divergence on the horizon is radiation. It's modes that are tangent to the horizon or transverse to the propagation direction of any, they're kind of transverse modes as far as any photon falling into the black hole is concerned. And so what this equation is saying is that a time change of the radial component, the Coulomb field of the electric field, inevitably gives rise to radiation modes that then will propagate into the black hole interior. Now, Alice is doing everything very slowly, so her potential is changing very slowly. That means that the electric field sourced on the horizon can be very small. But nevertheless, because there's a net change in the position of her particle, there has to be a net change in the Coulomb field registered on the horizon. So that means that even though at any given moment in time, E sub A, the kind of electric field, the tangent electric field on the horizon might be very small at any given time, I can't approximate it by zero because it has to integrate up to a finite number in order to give rise to a net change in the Coulomb field. But that means that since E sub A is the time derivative of A sub A, there has to be a net change in the angular components of the four potential that cannot be neglected for a consistent description of the problem. So in pictures, there has to be a net displacement between early and late times of the four potential on the horizon. And of course, the four potential is gauge dependent, but changes in the four potential are gauge invariant. And this will look familiar to anyone who studied the electromagnetic or gravitational memory effects. This is a mathematical analog, exact mathematical analog, but on a black hole horizon. And unlike the memory effect at null infinity, this occurs in all number of space-time dimensions. So this displacement of the four potential gives rise to a low frequency behavior that diverges at, in the Fourier transform that diverges at low frequencies. So basically, you have some step function like behavior, you're going to get a 1 over omega piece in the Fourier transform of the 4 potential. But if you compute the number of photons produced due to such a 4 potential through the horizon, the form of the number, the form of the Klein-Gordon norm, which computes the number of photons, dictates that any such 4 potential that undergoes this displacement diverges. So there's an infinite number of these photons, even though they're very low frequency, arbitrarily low frequency, there's an infinite number of them. This is going to give rise to an infrared divergence. Now, of course, in the real experiment, Alice displaces, creates a superposition, and then brings it back together. So there'll be some finite time interval, delta V. But still, there's going to be some growing number of soft photons that are produced. And this number of soft photons is going to grow like, delta, is going to grow like n down here, expected value of n. There's going to be a logarithmically growing number of soft photons lost behind the horizon. And this is just due to the fact that she moved the particle at all. So it's an unavoidable effect. And more than that, as a function of Alice's proper time, the difference between the branches of her experiment sources a number of photons that's growing linearly in her proper time. I say it was growing logarithmically, but that was in terms of time on the horizon. There's the surface gravity and an exponential factor convert the logarithmically growing affine time on the horizon into linear growth of time here. So, okay, very good. So if I plug in numbers, we find that Alice's decoherence goes like the following rate. And if our sun were a black hole, an electron on Earth superposed by a meter would decohere in 10 to the 32 times the age of the universe. So I would not say this is an effect we should worry about. But if the experiment were done close to the black hole innermost stable orbit, it would decohere in about 5 minutes. So, that's still probably smaller than the effect due to the whatever accretion disk might be near an astrophysical black hole, but the effect can be large if you're close to the black hole. And of course, there's an analog in linearized quantum gravity, which is even weaker, but maybe more interesting because all objects source gravity and gravitational fields can't be shielded. So there's no way to avoid sourcing superposed Newtonian fields inside the black hole. And so there's a universal decoherence, at least due to quantum gravitational effects. And for the last section of the talk, I'll just mention this upcoming work, which is that so far, from Alice's perspective, you can recast all of this in the language of quantum information theory and exact or approximate quantum error correction. So imagine that you can understand the effect of the black hole as some quantum channel acting on Alice's superposition, and you can compute the fidelity between her initial and final states, given that she's been decohered by this quantum channel. And even give her an optimal recovery channel D. And this fidelity is going to describe her decoherence. So for clarity's sake, in the discussion, I'm going to use the Holevo fidelity, which is just some technical detail. It makes the calculations easier, and you can show that it's a very good approximation to the kind of more standard Ullmann fidelity. But okay, that's some nice mathematical formalism. But I'm going to now tell you this is related to the story I told you at the beginning about blobs hiding in the interior of the black hole. Because, yeah, so okay, then this is my last slide, so I'll just say that. The punchline is the trace distance, it gives a measure on the distinguishability of states on the interior, but for an optimal possible measurement. And for Bob in the black hole, for any imaginable Bob, this bounds his ability to resolve states on the interior. But the trace distance is tightly bounded by this fidelity. And so what we show is that as a function of time, as the fidelity, as Alice's particle decoheres, the ability of any optimal measurement on the interior grows in such a way that they're actually equivalent. So the decoherence of Alice is equivalent to the probability of an optimal measurement on the interior of the black hole to resolve the difference between the field states that are set up by Alice's experiment. So decoherence due to the black hole is equivalent to the decoherence due to optimal measurements performable in the black hole interior. So that's basically it. And I probably don't have any time for questions, but thank you very much.
Thank you, then.